Hi everyone, and welcome to this video. I am seriously excited about today's topic because we are going to fundamentally change how you view the words fuel and energy. We're taking a journey today, a complete concept to application journey starting right at the gas tank of your car and zooming all the way down to the molecular thermodynamics of combustion. Our goal is to totally demystify what's actually happening inside an engine, and we are going to do it using the precise paradigm shifting concept that engineers use to measure true efficiency. So let's dive in. So here's our roadmap for today. First, we'll cover energy versus exergy. Second, balancing methane and air. Third, the adiabatic flame temperature. And last but not least, the heating values and efficiency. Alright, part 1, energy versus exergy and the car fuel analogy. There is a massive, sharp line between two concepts that we honestly use interchangeably way too often. According to the first law of thermodynamics, energy is always conserved, no matter what. Imagine an isolated box with some fuel and air in it. If that fuel burns, the energy isn't actually lost. It's just transformed into a slightly warm, totally useless mixture of exhaust gas. The total quantity of energy is exactly the same. But exergy? Well, exergy is entirely different. Exergy is the actual potential of that system to do useful work, like turning a wheel or generating electricity. And unlike energy, exergy is permanently destroyed by the irreversible nature of combustion. To really ground this heavy physics into your everyday life, think about this quote. When you fill an automobile's fuel tank, it is the exergy that you seek and for which you pay. You aren't paying for conserved energy that just turns into warm, useless exhaust at the tailpipe, right? You are literally paying for the chemical potential, the exergy, to push your 2-ton vehicle down the highway. Once that potential is used up, it's destroyed forever. Its economic value goes to absolute zero. Okay, moving right along to section 2, balancing methane and air to release that exergy. Let's start with the absolute simplest, most ideal scenario imaginable. We want complete combustion of a super common fuel, methane or CH4. For complete combustion, all the carbon in the fuel has to burn to form carbon dioxide, and all of the hydrogen has to burn to form water. If we just apply basic conservation of mass, we see that one single molecule of methane needs exactly two molecules of pure oxygen. The result? One molecule of CO2 and two molecules of H2O. It's neat, it's tidy, and it balances perfectly. But of course, there's a catch. The catch is that in the real world, we do not have tanks of pure oxygen hooked up to our car engines or power plants. We use regular atmospheric air. This brings us to a really important concept, the theoretical amount of air. This is defined as the absolute minimum amount of air needed to supply just enough oxygen for complete combustion. No more, no less. But because we're using air instead of pure oxygen, we are introducing a massive new variable into a perfectly balanced equation. And here is that massive variable. Our source idealized dry air as 21% oxygen and 79% nitrogen. What that means in practice is that for every single part of oxygen we desperately need for our fire, we are forced to drag along 3.76 parts of heavy, completely inert nitrogen. So, to get those two parts of oxygen, we need to burn our methane. We literally have to pull in 7.52 parts of nitrogen. This nitrogen doesn't do a thing to help the fire. It's just going along for the ride and it drastically blows up our air fuel ratio. Which leads us perfectly into section 3, the adiabatic flame temperature or reaching the thermal limit. So the absolutely crucial point here is defining our thermal limit. The adiabatic flame temperature is the absolute maximum temperature the combustion products would ever reach if we had zero heat transfer to the surroundings. Meaning, imagine the walls of our engine or reactor were perfectly insulated. Engineers care deeply about this theoretical limit because it tells us the absolute maximum thermal stress our engine materials will ever have to face before they, you know, melt away. Now, think about this for a second. What happens to the temperature inside of our combustion chamber if we decided to pump in way more air than that theoretical minimum that we just talked about? So, our natural everyday instincts would say that if you blow more air on a fire, the fire will get bigger and hotter, right? Well, that's the logic. Well, let's see what the thermodynamics actually dictate. The answer is actually incredibly counterintuitive. It turns out that the absolute maximum adiabatic flame temperature hitting around a blistering 2300 Kelvin happens at exactly 100% theoretical air. So when you supply just enough oxygen and not a single molecule more, that is when you get the highest possible temperature. But watch what happens when we pump in excess air. As the mixture dilutes, the maximum potential temperature absolutely plummets. If we pump in 400% of theoretical air, the temperature drops all the way down to 950 degrees Celsius. I'm sorry, 950 Kelvin. Why? Well, remember all that heavy nitrogen we talked about earlier? All that excess air acts as a massive diluent. The heat of the fire literally has to work to warm up all that extra, completely unnecessary gas. This drastically cools the overall temperature of the products and subsequently permanently lowers the energy available to us. And finally, section 4, heating values and efficiency. Now let's take a look at the final scorecard. In the real world, engineers use heating values to approximate the chemical exergy of a fuel. We generally compare the higher heating value or HHV or the lower heating value LHV for common fuels like liquid octane or gaseous methane. The difference between the two really just comes down to whether the water produced during combustion condenses into a liquid which releases more heat, giving you the HHV, or if it stays a vapor, giving you the LHV. But the biggest takeaway here is that these standardized numbers are exceptionally practical approximation of the total chemical exergy locked inside the fuel that you're buying. So, how well do our modern, highly engineered machines actually use that potential? We can take a look here. We have an example of an internal combustion engine. So, when all the math is completely done, accounting for the exergy destroyed during the combustion process itself, the exergy carried out and lost with the hot exhaust and stray heat transfer, the exergetic efficiency of that engine was calculated to be just around 40%. That means 60%, well over half of the fuel, precious exergy, the actual potential for work that you pay your hard earned money for at the pump is permanently destroyed or lost to the environment. There's no way around it. It really kind of changes how you look at a running engine, doesn't it? So, before I end this video, I'd like to leave you with this provocative thought to chew on. Now that you know the fundamental difference between energy, which is just happily conserved, and exergy, which is that precious, fragile potential for useful work, where else is potential being permanently destroyed in your daily life? Whether it's an inefficient water heater in your basement, a poorly insulated house, or, you know, even how we manage our own time. XGG analysis is an incredibly powerful lens for seeing the world. So that's all for this video, and thank you so much for joining me.